mathematically characterized. So just to fix the notation, I will recall the general problem, the one of supervised learning, in which there is an unknown relation that we want to study that could be the corrected labeling of some pictures. And we don't want to write down explicit algorithm to do that for the specific G, but we want to learn starting from examples. And so the first ingredient that we need is a training set in which some examples of correct labeling are provided. The second ingredient, of course, is a class of candidate function in order to try to imitate the original G. And this is typically a parametric class of function. In order to select the best function in this family, what we do is typically to define a cost function. In this work, we will consider the quadratic one, and we try to minimize it. So we try to minimize the error on the training set. So the strategy of the training is in two steps. The step 0 is to initialize randomly the parameters, because we don't want to encode the solution already in the initial choice of the parameters, but we want to find the solution variationally by the training. And in particular, the second step of the training, in this case, will be the training of the parameter using gradient descent, so a way to minimize the error at each time step. So the question that we want to try to answer is, what will be at the initialization and during the training the function generated by the quantum neural network that I'm going to define in the next slide. But before, I would like to introduce some problems that may arise in this setting. First of all, and this is very general because it might happen in principle also in the classical case. So the cost function in general is strongly non-convex, and therefore this minimization could not be successful. We could get stuck with the gradient descent method in a local minimum, which is not the solution that we're looking for. But furthermore, there is a doubt about expressibility, because if the number of degrees of freedom is not large enough, the global minimum, provided that we reach it, might not be 0. And so the family might not be able to fit not even the training set. So a strategy could be to try to give more and more degrees of freedom, increase the number of parameters. But then there is another risk in the over-parameterized regime, which is the one of overfitting. So yes, we have enough degrees of freedom to provide a perfect fit of the training set, but then on the rest of the input space, there could be a completely wrong answer. So in the classical setting, this regime, the over-parameterized regime, so the regime in which the number of parameters is way larger than the number of examples, turned out to be somehow successful. And these two papers provided the first mathematically rigorous explanation why this is an interesting regime. And so what we want to do is to try to answer this question in the perspective of the over-parameterized regime. So let me now define the model that we are going to consider. We start from an initial fixed state. We apply to this state a parameterized circuit in which layer by layer we encode using parameterized gate the trainable parameters, and we make the qubit interact. And furthermore, we are free to encode wherever we want with other parameterized gate the input of the machine learning problem. At the end of the circuit, we have an observable, which is a sum of single qubit terms. The total number of qubits will be called M, this notation, M. And the output, the function generated by the quantum neural network, will be the expectation value at the end of this circuit of the observables computed on the final state, up to a normalization that I will introduce soon. So, given an architecture with these properties, what are the main quantities that we should keep in mind during this talk in order to understand the hypothesis of the theorem that I'm going to state. First of all, the number of layers of the circuit, and this number of layers might depend on the number of qubits, because we are going to consider a limit in which the number of qubits, in order to make the circuit over-parameterized, will go to infinity. And so we do not exclude the cases, which are the most interesting, I think, in which the number of layers is not fixed. So the second important quantities are the past and future light cones, in particular the maximal cardinalities that they have in a given architecture. So just to, as a reminder, the future light cone of a parameter is the set of observables depending on that parameter, and the past light cone of an observable is the set of all the parameters which are relevant for the final computation of that observable. And finally, as I said, the normalization is the last important quantities of the architecture. And this normalization is chosen so that in the limit of an infinite number of qubits, the covariance of this function, covariance because the parameters are randomly initialized, will be order 1. To have just an intuition about the need of this constant normalization, constant if m is fixed, it's in the case when we sum IID random variables. In that case, you perfectly know that the normalization that we need is 1 over square root of m in order to have a non-trivial limit. So let's start answering that question at the step 0, so when we initialize the parameters. Having a sum of local observables, we will have a function given by the sum of m different terms. And a naive approach could be, okay, maybe this is similar to the case of the central limit theorem, where we have IID random variables, we consider the sum, and the limit is a Gaussian random variable. But of course, we have two problems to take into account. First of all, here we have function. We don't have only random variables. So we need to define a sort of Gaussian distribution generalized to function, but this is just a technical aspect. The crucial aspect that we have in these quantum circuits is that these terms, which are random variables because they depend on the random parameters, are not necessarily independent. And this can be easily seen in this example, in which, considering two observables, they might have in the circuit some common parameters, and therefore they cannot be independent. And so we will need to take into account all these dependencies. So for the first point, the definition of a generalization of the Gaussian distribution to function, well, we have to introduce the notion of Gaussian process that maybe you already know. Whenever we have a family of random variables, which might be infinite, the index here may belong to an infinite set, we say that this family is a Gaussian process whenever we have the following property: if we take a finite subset of this family of random variables, the joint distribution of this subset is a joint Gaussian distribution. Concerning the dependencies, the technique that we use to study this case is the one provided in this reference, and this is the technique of dependency graph. So we applied this, I would say, generalized version of the central limit theorem to the case of quantum circuits. So what we need to do to study the probability distribution of the sum of these terms which are not independent is to study and consider the dependency graph, all the dependencies. This is just an example for this circuit of the case that we are studying, in order to have some hypotheses to bound the non-Gaussianity of the final distribution. And in particular, our first main result of this work is that whenever the light cones of a given architecture are narrow enough asymptotically compared to the normalization, then the initial output distribution of the quantum neural network will be a Gaussian process. So what about now the training? What can we say about these doubts and these potential problems? First of all, a necessary step is to try to understand what this evolution equation for the parameters means in terms of the model itself. So we can just use a simple chain rule in the derivative in order to translate this equation into a differential equation for the function. And as you can see, the protagonist of this evolution is this quantity, bivariate function, which is called empirical neural tangent kernel. And it makes, as you can see, the solution, the analytical solution of this equation very hard because there is a time dependence here. So if this was constant, it would be easy to solve the equation, but it is not the case. So what can we do in order to give an answer to the question? Well, the first ingredient is to prove that in the overparameterized regime, the training asymptotically belongs to a really small portion around the initial parameter. So given any initial parameters, at least with high probability, the evolution will be confined into a really small region. And therefore, it makes sense, at least heuristically, to consider the first order Taylor expansion of the model and say, okay, this might be a good approximation of the original model because the displacement in the parameter space is very small. Why is it interesting to study this model, which is not the original one? Well, because the differential equation for the evolution of this model becomes easy to solve. Indeed, here we don't have any more the time dependence, and therefore we can write down the explicit solution for this differential equation. So the final ingredient is to prove that our intuition of having a good approximation with this first order Taylor expansion is a good intuition because asymptotically we can rigorously prove that the two trajectory in the parameter space and the two function generators converges, and therefore the solution provided for the linearized model is asymptotically the solution for the original model. And this solution has two properties. First of all, it is it's maybe not it's not very easy to see it in this form, but it's not difficult to prove that it's a solution asymptotically in T fitting the training set. So it will provide a good fit of a perfect fit of the training set. And second, it's a linear combination of the function at initialization. So it's a linear combination of Gaussian process, and therefore it's a Gaussian process itself. So the theorem that we proved is that under the hypothesis of narrow light cones, and assuming, of course, that we are not choosing a pathological circuit for which this quantity in the differential equation, the neural tangent kernel, do not exist or is not invertible. But this is a bit pathological, I would say. Then we have the perfect fit of the training set. So the cost is exponentially decreasing in time. And we know the probability distribution of the function generated, which is regular. So it will not something strongly dependent on the number of parameters on the initialization point. On the contrary, it will be independent asymptotically on the initialization, and independent and more regular. It will be indeed a Gaussian process as the overparameterized regime is achieved. So concerning these three doubts, we have some answers. The initial Gaussian process will be a new Gaussian process perfectly fitting the training set, and this is at least an answer about the regularity. Of course, we are not talking about the generalization performance. We are not discussing how well it could fit the rest of the original function. But at least it will not be strongly irregular. In the quantum case, differently from the classical case, we have a further point, which is the noise, statistical noise. Indeed, the model function is defined as an expectation value of a quantum observables. And therefore, the model itself is not known unless we perform an infinite number of measurements to provide a perfect estimator of this expectation value. And therefore, the differential equation that we studied in practice is not this. It's a discrete time evolution with an estimator of the gradient of the cost function. But we proved that in order to retrieve all the previous results about trainability and regularity, this bound on the variance is sufficient. But it looks really complicated, but what does it mean? Well, it just means that in order to have an epsilon small error at the end of the training or at the time t star, the number of measurements will be bounded by this really rough estimate, which is polynomial. These quantities are just polynomial in the number of qubits, so a polynomial number of total measurements in order to train the quantum neural network is sufficient, taking into account this statistical noise. So I will just spend one last minute talking about the problem of Barren plateaus that you probably already know. When the cost function is very flat, then we do not expect these models to be trainable. But the first thing that we have to notice is that this phenomenon will be associated with a exponentially decreasing normalization constant using the results of this paper in the number of layers, exponentially decreasing in the number of layers, and therefore, whenever there are Barren plateaus, so this is also exponential in the number of qubits, we can see, it's easy to prove that our hypothesis will fail, and therefore we are not proving that when there are Barren plateaus, the quantum neural network are trainable. On the contrary, when we do not have Barren plateaus, there is some hope to have trainability, and more precisely, there are some examples of architecture which are trainable in the regime which is free of from Barren plateaus. If we consider a number of layers which is logarithmic in the number of qubits, and a geometry for the circuit which is not just the one-dimensional, but we consider, for instance, the two-dimensional square lattice of qubit with nearest neighbor interaction, or not necessarily nearest neighbor, but just this is to simplify. When epsilon is small enough, and the hypothesis of our theorem are satisfied, and furthermore, this non-trivial geometry will make the circuit at least not classically computable in a simple way. So we don't know so far some simple way, and in general, we don't know any way to compute classically in this setting what happens in the local Hilbert spaces defining each observable. So this might be, as an open question, an interesting setting to study to see if something can be said about the simulability or potential quantum advantages. So in order to conclude, I just want to say that in this work we have studied the overparameterized regime in which quantum neural network turned out to be a Gaussian process at initialization, turned out to be trainable and producing a regular function during the training. All these results are stable under statistical noise up to a polynomial number of measurements. And so the step in the future might be, first of all, to give quantitative bound to find the discrepancy of the result. So the discrepancy between the probability distribution of a finite site circuit and the corresponding Gaussian process. And we are working on these bounds in order to understand better the speed of convergence. A more subtle question would be understand the role of the finite size effect, if they have some properties, if they can help training, what is their role in the generalization power of the circuit. It will be very interesting finally to understand if there is a strategy, as I said before, maybe to classically simulate in this regime where it is not known for the moment, or if on the contrary, some particular architecture, some settings, some problems are suitable to look for a super polynomial quantum advantage in terms of quantum machine learning in this setting. Thank you very much for your attention.
All right, thank you very much, Filippo. And now we have some time for questions. Yeah, thank you.
Yeah, that was a great talk, so thank you. I'm sorry if you said this, but I didn't quite catch it. Did you say that the regime where barren plateaus occur is outside of the scope of your assumptions? So I was a bit confused how barren plateaus interact with
yeah, okay.
process.
So we already know that when we have barren plateaus, since we have very flat landscape, when we have barren plateaus, the quantum neural network is not trainable. So it will be a bit contradictory to say if there are barren plateaus, then our result is better. No, our hypothesis, the hypothesis that I said, that I showed in the theorems, like this hypothesis will fail because this normalization constant will be exponentially small, and so this limit will not be zero, it will be infinite. So when we have barren plateaus, we cannot hope to have all these, at least with our techniques, we will not have this result. In general, we will not have trainability. But there are, what I wanted to say in this slide is that there are some interesting regimes which are free from barren plateau. So in the regime in which L is logarithmic and epsilon is small enough, this normalization constant will not be exponentially suppressed. And in these regimes, our hypotheses are satisfied. So it's in that regime that we need to deepen the consequences of our result.
All right, thank you.
All right, I think we have time for one more question. In that case, I'll ask. So you pointed out that you observed this kind of lazy training, where the trained parameter is actually very close to the initial parameter setting. At the same time, you're also saying that training achieves a perfect fit. So somehow that means that if I randomly initialize close to that initialization, there's always a good parameter setting?
Yeah, because the solution to have perfect fit is not unique.
Right.
So I don't have a picture here, but you should imagine this landscape to be more and more full of local minima, which are global minima at the same time. And so wherever you initialize the parameters, you will be able to reach the global minimum, which is not unique. And all the quantities that appears in the solution will concentrate around their expectation value. So the solution will be globally unique, also using different parameters.
All right, very nice, thank you. Then let's thank Filippo again, and we'll continue in approximately 3 minutes. All right, thanks for coming back, everyone. Please take your seats so that we can continue. Calm down, guys. All right, so we've got the second talk in the last session of the day, and it'll be Daniel telling us about a connection between learning algorithms and circuit lower bounds. Take it away.
All right, thanks for the introduction. This is called quantum state learning implies circuit lower bounds. So let me adjust my mic really fast. It's joint work with Nai-Hui and Fang, who I believe are here attending. I don't know if they're in the room right now. It's based on this work that's on the archive, though I'll actually be presenting some updates from that archive posting. And yeah, so a very fundamental problem in quantum information is producing a state. So that's basically starting from, say, the all zero state. How much resources do you need to produce some target state? For instance, if you want to prepare the GHZ state and you're starting with all zeros, and let's say your gate set is Hadamard and CZ gates, you might produce it like this. If you have like a C0 and Hadamard gate set, you might like decompose it slightly differently, but the idea is the same. And in general, you can ask like, how many gates do you need to produce a state? That's like a very concrete question you can ask. And this is basically what's known as like non-uniform state synthesis. So just like a very like fundamental minimization problem that you need just based on some defined gate set. But another notion of circuit complexity is that of uniform state synthesis. So which is how much time do you need to find the circuit? And time might be a little vague for circuits, but so I'll tell you exactly what I mean. So let's say I have a list of states, so psi n, where n is just some natural number. And if I tell you some natural number, how much time do you need to synthesize psi sub n? So n is some parameter that grows. So now we can talk about time as complexity, like some growth function. Like, do you need linear time? Do you need quadratic time? Do you need exponential time? And that's why we need this natural number, similar to like functions and problems in CS. We need to sort of have this notion of like what is the size of the problem, because asking like what is the time to produce the GHZ state, that doesn't really make too much sense. It's like a fixed number of qubits. You can just like output this in like 0 time, basically. Okay. And we can take this a step further. So now we have a notion of time. We can introduce notions of like complexity classes. So you're probably familiar with P and NP and BQP if you're at this conference. So something you can define is this class called state BQP. It's basically the set of all of these kind of state sequences that you can produce in polynomial time. And you can sort of think of this like state BQP as a characterization of problems with classical inputs and quantum outputs. So we have the same kind of bit string input, or you can generalize this to bit string inputs, and we have some quantum state as our output. So like a new kind of problem that is not characterized by normal classical complexity theory. So yeah, there's like a slightly more formal definition. You add mixed states. You have like this bit string now instead of just natural number. You only approximately create the state, so you have some robustness. But that's just details that you shouldn't actually worry too much about. And I just want to add that like these state complexity classes do actually behave somewhat similar to the normal complexity classes that you might be familiar with. So there's a very fundamental result in a classical complexity theory that P space equals IP. And it turns out that it was proven last year by Mecker and Yuan that state P space equals state QIP. So there's like this fundamental connection that still exists even for these new kinds of quantum problems. And so basically, something that I want to do is using this language, I want to talk about this like one bullet point intuition, which is that states that are harder to produce should be harder to learn in general. And this basically follows from what we know about classical Boolean functions in that like Boolean functions that are more expressive, that are more powerful, should be harder to learn. So some quantum examples is we have things like product states, stabilizer states, now constant depth circuits. These are like very, very easy to produce states. And these are the ones that we actually have learning algorithms for. And then some hard examples would be hard random states, like T designs that are super polynomial. These are hard to produce and hard to learn. So, and basically, can we formalize this connection? Like we're theorists, we have like intuition, but our goal is to basically formalize these intuitions for people as actual theorem statements. And the takeaway of this talk is that there are ways to formalize this, and I'll go into exactly what I mean by that. But the idea is that slightly non-trivial learning algorithms should imply new results about state synthesis. That's like a takeaway message of our work, and there's like some framework that we show that works in a variety of ways. And to do that, we're actually going to do a lot of things. We're going to have to use complexity theory to talk about state synthesis, learning theory, obviously, and then we're actually going to have to take a path through cryptography to actually show these results. So what do I exactly mean by quantum state learning? I really mean it in like the traditional tomographical sense. So just given multiple copies of some unknown state rho to produce a rho hat that approximate this, like some classical description. And it's known that this requires an exponential amount of samples and time in the worst case. So this is a known hard problem. And so generally what we do in the learning community is we make assumptions about the data. Like there's some no free lunch theorem. So we actually have to start making assumptions. And some assumptions we might make are things that are produced by from circuit class, ground states of Hamiltonians, matrix product states, things like that. And basically, a more formal version of our result is that if you can do like 2 to the slightly under linear samples and 2 to the poly time quantum state learning algorithms for states produced by some concept class C, this will imply learning like lower bounds for state C. That seems somewhat vague, probably, to most of you. So, okay, a more concrete example is, let's say we have non-trivial learning algorithms. So basically the same parameters that I showed you before for states produced by this circuit class called QTC0. You don't have to know exactly what QTC0 is just yet, but basically our results would show that either one of the two is true. So either state BQE, where BQE is this like exponential linear time, is not contained in state QTC0, or for every k greater than or equal to 1, there's this following separation between state BQ sub x and state BQ size. If you're not really familiar with circuit like complexity lower bounds, this might not seem that interesting to you, but it turns out that in general, like showing circuit lower bounds is a very, very hard problem. If you're not aware, like there's only like we only really have results for these very, very weak classes to not be in like NX and things like that. These are like fundamental results in classical complexity theory by Ryan Williams and his students. So it's like very, very difficult to prove lower bounds, and this is basically in one direction saying that there's like a path to prove it via quantum state learning. And I guess I sort of did this out of order, but I want to say that, emphasize that these parameters that I put out, the 2 to the n to the 0.99, is like just slightly non-trivial. And the reason for that is that I told you before that you can do tomography in 2 to the theta n samples in time. And also via shadow tomography, any class produced that's like efficiently producible by a polynomial sized circuit can be done using shadow tomography with like super polynomial samples and like 2 to the super polynomial time. So if you can either reduce the time or the sample complexity of brute force tomography, or reduce the time of shadow tomography even just a little bit, you'll imply some like interesting non-trivial circuit lower bounds. And I should emphasize that this like 0.99 is not like specific to 0.99. It's just some concrete number that's less than 1. Okay. As a bonus, I was talking about like state complexity classes before, but we also proved things about decision problem versions, like the traditional complexity classes. But I actually won't really go into this in this talk. But you can ask me about that later. Okay, so where does cryptography come into play? Well, a general property of a pseudorandom object, which is inherent in cryptography, is that they're efficient to construct, but they're hard to distinguish from true random. So naturally, pseudorandomness is like at complete odds with learning. This is why things like learning with errors and learning parities with noise are like the fundamental cryptographic hard results. And you can see this basically an informal statement is that hard to distinguish from random implies hard to learn. And you might formally know this as like a generalization of the no free lunch theorem and things like that. So on the quantum state side of things, there's this concept called pseudorandom states that have been talked about, I think, throughout this conference by Tomoyuki and others, which is a quantum state that looks hard random, but is easy to produce. So therefore, it's actually very far from being hard random, but cannot be distinguished from it. And the no free lunch theorem naturally holds for this. It's not too hard to prove. And basically, a very dream goal of ours would be to say that if pseudorandom state ensembles exist that have really strong security, so they're secure against like very, very strong adversaries, but they're also efficiently synthesizable, then any non-trivial learning algorithms for a circuit class C would imply the following circuit lower bound. So it's basically saying that this pseudorandom state is in state BQP because it's synthesizable in polynomial time, and it is not in state C. And the reason for that is that because you can learn state C, that means that state C cannot produce pseudo-random states. So therefore, it's in BQP, but not state C. Does everyone see that? All right. If you don't see that, then you get lost a little bit later. Okay. Any questions? Okay, good. And I should note that this is achievable with some strong cryptographic assumptions, such as sub-exponential secure LWE. This is how some other works, I think by Matthias and others, basically work. And that's all fine and good. But basically, all of the results in this vein rely on LWE or things like that. And while I'm not saying that LWE is necessarily like easy, I'm not making such a claim, but like it would be good that we don't rely on just one assumption for all of our hardness results. Like we would maybe like try to get evidence in other ways, right? Like branch out a little bit. And one of the highlights of this talk is that we're going to get these kinds of hardness results without making any cryptographic assumptions. So the goal is that can we produce pseudo-random states without making cryptographic assumptions like one-way functions and things like that, or LWE? And okay, yeah, I guess the highlight of this talk is that it turns out that you can sort of make such statements, but they're not quite as strong as what we would hope for. Let's see. Okay, this kind of went out of order, unfortunately. But the main thrust of our work is to show the following, that if state, like this weird p-space size class that I'm not actually going to define, but is quite related to state p-space, is not contained in state BQ sub x. Basically, there's like some state synthesis separation that implies a pseudo-random state ensemble. And it has the following parameters. Unfortunately, it's synthesizable in exponential time instead of polynomial time, but it is secure against sub-exponential time adversaries. And that's really the goal of ours. And basically, this PRS can be turned into a state sequence without too much effort. And basically the following set of like logic that we applied before applies now, except now we have state BQE for this 2 to the exponential, or 2 to the theta n time, rather than state BQP because polynomial time. Okay, so this relied on this particular complexity theoretic assumption. Something else we do is we show that if the other assumption is true, like if either it is contained or is not contained. So if it is in fact contained, then we show a different circuit lower bound. It's not too interesting, I think, but it's basically why we have 2 bullet points in our statement. And if you want to know more, it involves the following ideas from complexity theory, like BQP is in p-space, quantum state discrimination, circuit size hierarchy theorems, and things like that. Okay. So how do we actually build this PRS? Well, we basically rely on this great result by some of the audience members here, that if p-space is not contained in BQ sub x, then there exists a pseudorandom generator that has a very similar set of qualities than the pseudorandom state that we create. And so the goal is basically to turn this PRG into a PRS. There are some standard tricks to do this in the cryptography literature, but it turns out that because of the parameters of this PRG being a little non-standard, those techniques don't actually work in a straightforward way. This is why we had to introduce this class called state p-space size and things like that. In the interest of time, I won't go into the details, but you can again ask me about that later. Okay, and then I just want to add that there's also this notion of unitary synthesis that was introduced along with state synthesis, and that we can basically make similar statements about that. There's something called a pseudorandom unitary. We can construct pseudorandom unitaries based on these complexity theoretic assumptions based on unitary synthesis, which may be of independent interest. Unfortunately, we can't really write it up until Robert Huang and Fermi Ma finish their stuff. But yeah, I've talked to them in private. It should all work without too much issue. And this is like the formal statement, or slightly more formal statement, that slightly non-trivial learning algorithms for unitaries will imply circuit lower bounds for unitary synthesis. And the same is true for decision problems, and that requires a follow-up to the follow-up of the Robert Huang and Fermi Ma paper. So that one will take a while to come out. Yeah, so that basically wraps up what I wanted to say. So open problems are basically, can we tighten the parameters of this pseudorandom state or pseudorandom unitary that we create? Ideally, we would create these in less than exponential time. Like we want to get that down to polynomial time. Basically, it would lead to better and more interesting complexity theoretic separations. There's further connections to meta complexity that was in previous predecessor works for classical Boolean functions that we haven't really explored too much. And a call to the learning people here is, can you maybe actually create some of these non-trivial algorithms to instantiate some of these theorems? So basically, can you do slightly better than brute force or slightly better than classical shadows? Yeah, I will be finishing my postdoc in 2025. So if you have any positions, academic positions you think I'd be a good fit for, please let me know. And that's it.
Hey, thanks a lot, Daniel. And we've got some time for questions. I see one by Alex.
So in the win-win argument, apparently, okay, one of the sides you only need the classical assumption, right? And then you will show that it implies a quantum assumption. Can one hope for having just the classical assumption on the other side as well? Yeah, can you hope to have the classical assumption here as well?
So this one cannot work with the classical assumption, but this one does work if you just have the classical assumption. But then you have they're not. It's not like one or the. It's no longer win-win. Yeah.
Do we have more questions? I've got an ill-defined one. So I find this idea interesting of how you say you want to kind of get rid of cryptographic assumptions and you do it with this kind of win-win.
Mm-hmm.
Is this something that is applicable in other scenarios, or is it very specifically when you're aiming for circuit lower bounds? I mean, it's the only context where I've seen it, but
I mean, win-win arguments certainly happen in all kinds of proofs and things like that. Is there anything more concrete
So I guess I'm wondering whether we can replace pseudo-random, say, generators or whatever, obtained from cryptographic assumptions by these kind of win-win pseudo-random constructions in other scenarios. As I said, it's not quite well defined.
I think the answer is probably not. The win-win argument, like one side of the win-win argument is kind of specific to things that are like diagonalizable, I guess, in a sense. This is like a sort of a specific property of things that you can like count and grow in a certain way. So my understanding is that it's not generally applicable. Yeah.
Some more questions from the audience? All right. Then let's thank Daniel again for his talk. Okay, and we'll meet at past for the last one. it's on. All right, everybody, here we go. Last talk, last session. So we've already heard a lot about Barren Plateaus at this conference, and now Diego is going to tell us about what's new in Barren Plateau theory.
Okay, thank you, Matthias. Hi everyone. Thank you for staying here for the very last talk of the conference. I appreciate that. So I'm Diego, and I'm going to present our work entitled Showcasing a Barren Plateau Theory Beyond the Dynamical Algebra. So this is the menu for today. First, I will explain what are Barren Plateaus and why they are an issue. Then I will review some known sources of Barren Plateaus that appear in the literature in the last few years. Oops, sorry. And then I will move to the main body of my talk, where I will explain what are the recent developments in our understanding of Barren Plateaus and why we now essentially have complete and unified general theory for them. And this I will do it in two parts. First, I will explain what happens when the input state, the initial state to the circuit, or the observable, lies in the so-called dynamical algebra of the circuit. And then I will move to our paper where we relax this assumption and we allow for completely general states and measurement observables. So let's get started. Barren plateaus. So Barren plateaus have become a big issue for the success of quantum machine learning since their discovery in this seminal paper by the Google team. So what is a Barren plateau? So let's say we have a quantum state rho. We have an observable O with bounded norm, for instance, a Pauli observable. And then we have an ensemble of unitaries U, which may or may not be parameterized. In the setting of variational quantum algorithms and quantum machine learning, they are parameterized, but this is not needed for what I'm going to tell here. And then we want to estimate the expectation value of this observable at the output of the circuit. This is what's called a loss function in variational algorithms that you want to minimize the expectation value. So a Barren plateau is an exponential concentration of this expectation value around the average value, which is typically 0, as the number of qubits increases. So more formally, we can say if the variant over the unitaries in my ensemble or over the variational parameters theta is exponentially suppressed with the number of qubits, then we have a Barren plateau. Whereas if the variance is at most polynomially decreasing, then we do not have a Barren plateau. So why is a Barren plateau a problem? So one can readily see from Chebyshev inequality that the probability of the expectation value deviating a quantity epsilon from 0 or from the mean is upper bounded by the variance divided by epsilon squared. So if the variance is exponentially small, then unless epsilon is also exponentially small, then we have an exponentially small probability of seeing any deviation from 0 from the average. But of course, on a quantum computer, we just have a finite number of shots for estimating these expectation values. We have a finite precision. And in particular, the error goes as 1 over the square root of measurements if you're sampling, or 1 of them over the number of measurements if you do something more fancy like amplitude estimation. But in any case, if you are in a Barren plateau, you need an exponential number of shots to actually resolve these problems and see any deviation from 0, which of course you cannot do when the system size scales. So now let me review some known sources of Barren plateaus. So it is well known that the expressivity of the circuit can cause a Barren plateau. So if your circuit is a 2D sign over the unitary group, then we will have a Barren plateau for any rho and any O. Moreover, if your initial state is very entangled, if it follows a volume law, then we will also have a Barren plateau. And then finally, the globality or the bodiness of the measurement operator can also induce Barren plateaus. So in particular, if we have these 1D brick layer circuits where each 2-qubit gate is a 2D sign over the unitary group, then whenever we have a global observable that acts on all qubits, then we always have a Barren plateau for any depth. Whereas if the observable is local, it only acts on a fixed number of qubits, then we avoid Barren plateaus up to log depth. So these results are all great, but the problem is that they are mostly architecture specific. And as we will see, they are not true in general. They will not hold for any circuit architecture. So the goal of having a unified theory of Barren plateaus is, say, you give me any quantum circuit, any state rho, any observable, can I predict what is going to be the variance of this circuit? Is there going to be exponential concentration or not? And for this, we will consider circuits of the written in that very general form up there, where each gate is written as the exponential of a Hermitian operator, Hj, with a parameter theta j. And when we have these circuits, we can define the so-called dynamical algebra, which is just the real vector space spanned by all these Hjs, so which are called the generators of the circuit. And this algebra, of course, is going to be a subalgebra of the unitary algebra. And if you're not familiar with these dynamical algebras, you can think of them as telling you what is the ultimate expressivity of your circuit. And to gain some intuition of why this is the case, you can think of the BCH formula. So say you have two quantum gates consecutive, so the product of two exponentials. This can be written as a new exponential where the exponent is just a linear combination of all these nested commutators. So examples. Say we have a circuit like this one with single qubit gates. Here, this is, why is this stand for the generators? So this H is there. So this is an RC rotation with parameter theta, and so on for the rest. So here we have single qubit things. So we have C, Y, we commute them, we get X. So we get all the single qubit Paulis, we get SU2. And we have that independently in time. So we just have this direct sum. Another example, which will be very important later, so keep that one in mind, is that of parameterized match gate circuits. So here we just have RC and RX rotations. And it can be shown that this algebra is isomorphic to the special orthogonal algebra, SO2N. And finally there, say we add to these circuits RY rotations, then we make the circuits universal. Therefore, the algebra is SU2 to the N. So the goal, again, of a unified theory of Barren plateaus is you give me a circuit architecture, you give me a dynamical algebra, and then you ask, what is going to be the variance of the expectation values at the output of the circuit? And there was this paper from 2021, I think, by Martín Larocca and Marco Cerezo and some other folks at Los Alamos, where they conjecture that this variance should be proportional or inversely proportional to the dimension of the Lie algebra of your circuit. And this result was proven recently, last year, in two independent and simultaneous, basically, papers. The one on the left is by the team at JP Morgan, and the one on the right is again by Martín Larocca, Marco Cerezo, and some others like Michael Ragone, and so on. So what they prove in this paper, more precisely, or what they give is an exact variance formula for the expectation values of the output of the circuit. Whenever rho, so the state, you can take out the trivial part, the identity, the component in the identity. So when rho is in the algebra or the observable is in the algebra, and your circuit is a 2D sign over the Lie group associated to your Lie algebra, then they are able to give a closed formula for the variance. And the formula looks like this here. So let's try to understand what it means. Say we have our dynamical algebra G. We know it's a subalgebra of the unitary algebra. So it is reductive, which means that it can be decomposed into a direct sum of so-called ideals, where the last part is abelian. That doesn't matter. Just keep in mind you can decompose it as a direct sum because this is a subspace of operators, simply. And then we have, in the variance formula, we have a sum over all these components of the algebra. So to further understand this, let's say that G is simple. This only means that there is only one component in the direct sum. So there is, it doesn't break down. So for instance, the unitary algebra or the special orthogonal algebra or the unitary symplectic algebra, these are all simple. Then the variance has this form: G purity of rho, G purity of O divided by the dimension of G, the algebra. So here we see that in the denominator we have the dimension of the algebra, and that's why the previous conjecture is proven for the case when rho and O are in the algebra. And then we have these other things, the G purity of rho and the G purity of O. So let's see what these are. These are essentially a measure of what is the support of the observable or of the state in the algebra, how much component you have there, how pure your states are in the algebra. And in particular, these are measures of so-called generalized entanglement, which were introduced in this paper in 2004. So what is this? Say we have a given operator subspace that has an orthonormal basis Ds. Then the purity, the S purity of an operator H can be computed with this formula. Basically, what you're doing is you're just orthogonally projecting to your operator subspace and computing what is the component that you have in that subspace. So with this, we can see that, for instance, if the dimension of your Lie algebra is exponentially large, then you're going to have a Barren plateau. So if your circuit is very expressive, but in a more precise way, as you know, it was known before. But also, even if your algebra is polynomially small, if your initial state or the measurement operator have very little component in this algebra, then you're also going to have a Barren plateau. So this is a rho and O dependent statement. Sorry. Okay. So now let's see how can we relax the assumption of the state and the observable belonging to the algebra. That's what we did in this paper. And for this, we had to resort to parameterized match gate circuits that can be created by layers of this form, as I said before. And even though here we restrict to parameterized match gate circuits, I will argue that all the elements of a final completely general theory are already here in this case, in this example. So let's see how this goes. Okay, yeah, as I said, the algebra now is isomorphic to the SO2N, and for the rest of the talk, the Majorana operators are going to be key. And in Jordan-Wigner representation, these are just Pauli operators. These ones here, they all anti-commute. They are just X or Y's padded with C's on the left. And so for an n-qubit system, we have 2n Majorana operators. And these are two key facts about Majoranas and match gate circuits that will be key to the theory or the general theory of Barren plateaus. The first one is that if you take the entire space of linear operators, so dimension 4 to the n, then this operator space can be decomposed as a direct sum of orthogonal subspaces that we call BK, where each BK is spanned by the product, by operators which are the product of K Majoranas. So if K is equal 0, we have the identity. If K is equal 1, we have all the Majoranas. And if we have K equals 2, we have all the possible products of 2 Majoranas. And in this case, B2 corresponds to the algebra SO2N. So this is the first fact. And the second one is that these BK subspaces, they are invariant under the adjoint action of match gate circuits, which means that if you take an operator which lives in one of these invariant subspaces, which are also called group modules, and then we act with a match gate unitary by conjugation, then what we obtain is something that is itself contained in the same BK module. And in particular, for all K except K equal N, these subspaces, they are not only invariant, but also irreducible. So with that, we can now state the main result of our work, which is a closed formula for the variance at the output of the circuit for any input state and any measurement observable. Again, whenever we have a 2D sign over match gates. And the formula is this one here. It has some formal similarity to the previous one, but it's different. So let's try to break it down. We see that now we have, again, these generalized purities, but with respect to the BK invariant subspaces in this case. And then we have the dimension of the modules of the BKs. And then we have a sum over all of them. So remember that here the algebra is just one of these modules. So whenever we had the previous case, we have this formula for the algebra, but now what we see is that when we relax the assumption of the observable and a state in the algebra, we have to sum over all these invariant subspaces with a term that is formally similar as the one before. So in particular, this implies that the conjecture that the variance is inversely proportional to the dimension of the algebra is false in general. Because what we have here is the dimension of the module, of the subspace your operator is in. And therefore, in general, yeah, the conjecture is not true. What matters is the dimension of the module you are in. And then we have these other terms. I'm not going to explain them in detail. I'll just say that these CKs, they correspond, they are covariances that appear. And I'll just say that they can only appear between modules that are isomorphic to each other. Okay, so some numerics to illustrate this general theory. The dots correspond to the numerical simulations, and the dashed lines are the theoretical predictions. So good agreement. We didn't screw it up. And so for a Gaussian state, here we take rho being the all zero states, and we're going to measure C tensor n. And this C tensor n belongs to the module B2n. So by the way, I didn't mention, but the dimension of these modules are at 2n chooses k, because they are spanned by the all products of k Majoranas. So you have 2n Majoranas, all possible products, 2n chooses k. So what we see here is that if m is a constant, like m1, 2, 3, then this variance is going to decrease polynomially. And if m scales with n, then this variance is going to be exponentially decreasing. And the interesting thing here is that for this case, C tensor n and C tensor n minus m is completely symmetric. It gives you the same variance. So you see that if we have C tensor n minus 1, so a very global operator that acts on all qubits but 1, we don't have a Barren plateau. So we have global observables that do not have Barren plateaus. So this, as I was saying before, this is why some analysis, previous analysis are not true in general, and we can see it here. On the right, it looks like the same plot, but it is not. Then there we have some non-fermionic state, and then we are measuring the operator xj, so single qubit x Pauli operator. It belongs to B to j minus 1. So again, if j is constant, then we don't have a Barren plateau. But if j scales with n, so say you're measuring x at the middle change, so at the middle qubit, then you're going to have a Barren plateau. So here we have the opposite. We have a completely local observable that nonetheless has a Barren plateau. And finally, here in the middle, we have a magic state. This one here, we are measuring the C1 operator, so one operator in the algebra. This state has an exponential extent. So if you decompose it into Gaussian state, you need an exponential number of them. And what we find is that the variance is polynomially decreasing. So at the beginning, we were excited because we were saying, oh, this is a magic state. This should not be classically simulable. Yet it doesn't have a Barren plateau. But it turns out we found a way to actually simulate this efficiently, not relying on Wick's theorem. So final thing I will say, just perhaps not very intuitive for example. Say you have your match gate circuit. Say you're going to measure in the middle qubit the single qubit observable C. This will not have a Barren plateau because it belongs to the algebra. However, if you measure x in that qubit, we saw before, we will have a Barren plateau. To go from C to x, you just need to add a single non-parameterized gate in your circuit. And a single non-parameterized gate at the end of the circuit can make a Barren plateau free architecture become or have Barren plateau, suffer from Barren plateau. Which so one has to be very careful what one is including in a circuit. Okay, so that was it. Outlook. After quite some effort, we now finally have essentially final Barren plateau theory for deep parameterized quantum circuits. And here, Lie algebraic techniques have been instrumental in this achievement. In particular, I recommend this excellent review by Larocca and co-authors about Barren plateaus. You can find everything that is known basically today in that paper. And I will finish with two open questions. First, what happens in the shallow regime? Because we've seen we need the assumption of being a 2D sign in order to compute these variances. And this is because we are using group theory and rep theory techniques. So can one find a formula for the variance in the shallow regime whenever you have not converged yet to a 2D sign over your Lie group? This is one open question. And then a very, I would say, pressing open question as well is what are the connections between the absence of Barren plateaus and efficient classical simulability? Because what we argue in this paper is that for many or most of the examples that we can come up with, except very contrived ones, which are based on source algorithm and things like that, then whenever we observe absence of Barren plateau, we also find efficient classical simulability. So this is an open question, but we argue here that this is the case, at least for many, many known architectures so far, or known applications, let's say, so far. So that was it. I'll conclude here. I will thank my amazing co-authors, Nahuel Diaz, Sujay Kazi, Martin Larocca, and Marco Cerezo, and I'll thank you for your attention.
My mic ran out of battery. We're also done with the conference, but if you have questions, please ask questions. Thank you. All right, any questions? Yeah. Thank you.
Thanks for the talk. So I think I missed it, but when you use the magic state, this state you put in, yeah, this one. You say it's classically simulable. Could you explain to me a bit more how you simulate it?
Yeah, for sure. I mean, preparing the state is not that you can, find a representation of the state itself classically efficiently. But the idea here is the following. The idea is that, okay, you prepare this magic state, which you cannot do classically. But then what you're interested in is applying afterwards a parameterized quantum circuit, match gate circuit, and estimate an expectation value. So the thing is that, for instance, here, you are measuring in the algebra. So all you care about is, and we saw that these match gate circuits have these invariant subspaces. So if I have something in the algebra, it will remain in the algebra. So I don't care about the entire state. I only care about each component in the algebra, which means I have this quantum state I prepared by a quantum circuit. So far, I cannot simulate anything. But then I know the algebra. I can measure in a basis of the algebra. So I get the expectation values, for the observables in the algebra. There are poly many. And then I can classically evolve this expectation, the action of the circuit, the variational circuit afterwards, or the match gate circuit afterwards. So in that sense, it's classically simulable, the effect of the match gate circuit on this state.
And did you try just like magic state like this one, or did you try like whole family of them?
No, we just tried this one. I mean, this was mostly for illustration purposes, and also to check that that things were working. So we thought each one of these examples showcases like something interesting, and yeah, we just tried this one.
Okay, thank you.
But I'll just say that given that we now have like a general formula, if you have the quantum state, you could compute what is going to be the variance for the state, because that's the point here. Like any state, any observable, you compute the variables.
Okay, thanks.
All right, more questions for Diego. So I remember a few years back, whenever I talked to Marco about Barren plateaus, he gave me like recommendations like don't use global cost functions.
Yeah.
So we had like simple recommendations to phrase. Now, based on your general theory, is the new way of recommending architectures just it's complicated because you have to like do all of this Lie algebraic computation to understand whether there is a Barren plateau, or are there still like simple rules of thumb that apply generally?
I mean, completely general answer is complicated. You will have to go to your group, find these invariant subspaces, and then check, okay, where is my observable, in which subspace, what's the dimension of this subspace, and so on. So completely general answer is it's complicated. But also, let's see. Yeah, I guess that's the main thing. Also, there is one thing that is interesting here. Like, this is true, but only if you go to log n. So in this case, we are not. Our theory says nothing. So this, in some way, this is an independent result because the theory is for like exactly. So in this regime and this regime, you are to design, and both observables, local, global, have Barren plateaus because the algebra, the circuit is universal. The algebra is too big. It's too expressive. So yeah, if you know the algebra, you can right away say you're going to have a Barren plateau if the algebra is too big. So that's, guaranteed. So that's our general recipe. You have like a very large algebra. Then you have a Barren plateau if you are deep enough. If you are shallower, then it's still an open question. But in general, but yeah. There are results, yeah, which are yeah, that's true. It's not. The approach is different in the sense that it's not Lie algebraic, but QCNNs is one example where it's known that they don't have Barren plateaus. But there is a very recent paper by Pablo and Paolo and some other people showing how to simulate yeah, these QCNNs with high probability. So yeah.
All right, thank you, Diego. Then let's use this opportunity to thank Diego and all the speakers of the session. And if I understand correctly, there's now some closing remarks in the main auditorium, so we might want to head over there.
Okay. Hi. Oh, thank you. I have just one question.